Hello YouTube, iFixItAll here, Team iFixItAll. We're going to get back on this iron. I've been doing some contemplating about how I'm going to make my connections. And I've pulled these conductors off and I've discovered a little bit of engineering behind it. So how many amps does this really pull? Well, it says it's 1,000 watts right on the iron back there. And also I wanted to cover something about the contacts we were looking at. These contacts that open and close that we were pointing out before. How does this really work? Because it has a potentiometer and there's a set of contacts in here. You go counterclockwise, that's off. In the previous video, I may have had a better angle of the dangle. You can see them getting pushed down. Now, let me demonstrate with my arms how this works, because this is a thermostatic dry erase board would be better. Okay, so one of the contacts, let me see if I can zoom out a little bit. So I was explaining to the wife when we were watching the video, there's two contacts. One straight, has a threaded rod going down, pushing it down. And one is kind of bowed a little, that has another contact on it. And what happens is, the electricity, when you're in an off condition, the two contacts are not touching. Well, that top contact represents the power coming from your outlet, the 120 volt leg. And this one is slightly curved. It still has a contact on it, but the metal that it's attached to is sort of arched. It's springy. So what happens is, when you adjust it to apply heat, you're actually applying power. And then it pushes down and it pushes down and it pushes down. If you've got it adjusted, this rotary potentiometer right here, if you have adjusted to the middle part, then here's what will happen. That arm will come down. It'll straighten that out the lower arm out a little bit. This arm will deliver power out to the heating element and come back around to the return path, which is the neutral. So what's happening is, when you're in the off state, you adjust it, you make contact. There's an arc that happens when you do that. There'll be one. You just won't never see it. That's why the contacts get dirty. And you adjust it, and it kind of tries to straighten this lower contact out. And as the heat builds up in the plate of the iron, it'll deform this lower arm even more, and it will act like a snap switch. It'll open. And as it cools off, it'll close. So when it opens, because it overheated, it's acting as a thermometer. It's controlled overheating condition. You're heating up that power going to the heating element. And as it heats up, it'll open. It'll remove power from the bottom of the iron. And as it cools off, it'll re-engage contact. So then you're done using the iron. This is going to follow each other, and at a point they're going to separate. Power will be removed. So maybe that's a better way than drawing it, but I'll do the two contacts here. One of the contacts has that. That's the straight one. That's 120 volt. And then this one below it is slightly deformed. And it will travel out to the heating element. Go through the heating element and to the return. So as that is pushed down, it'll send power through the contact out to the heating element and through the neutral. That's how that works. So it's actually not a potentiometer. It's a thermo switch that is also delivering power. And it is thermally controlled. That slight little arch is probably because that lower arm there is probably made of a bimetal, where the top layer might be one material and it might be two layers of metal, so that it reacts to heat, just like a regular thermometer does when you have one out on your front porch to see how hot it is or cold. It's because that little wound up wire is a bimetal. It's two different metals literally fused together so that they expand and contract at a different rate. Too much time on that. By the way, this is a homemade dry erase board. It's a piece of plexiglass with oil-based yellow on the back, just in case anybody homeschools. God, I spent too much time on that. So I've been studying this, and I was wondering, why did they engineer what they engineered as far as these connections? And I was looking at these lugs, which are really nice and high-end, but I noticed that they're stamped on the back with amp, which is Amphenol, and I don't think you'll even be able to see that. Another thing I noticed is that these wires were tinned. They're real stranded down here. Turn off the big light and see if I can get a better focus on it. They're very stranded down low, but yet it looks like they were soldered up through here. And then they transition into a brass lug, and I know it's brass because I cleaned it off with a wire wheel. And it's probably annealed and very hardened brass. So they were obviously concerned about heat translation from these studs up to here, up to this, from these connection points up through the harness, while it's inside this void of the iron, because the hot plate is low. It's going to radiate heat up. And that's why they had the heavy duty siliconized insulation rubbery stuff on the bare wire. What I don't know is, what is this soldering, what is this made of? Is it tin? Because they are tin coated wires. The backside does say amp right on the barrel. Now, if we stay focused in on that wire, you'll see it looks like it's been tinned all the way up. And it's the same on both. And when I say tinned, it could be solder or it could be actually tin. I don't know. But you can see the wire braids up here where there's no tinning. I watched the previous video and the whole focus thing was a big problem. It's everyone's problem. Turn on the big light. Oh, God, that thing is hot. I'm going to adjust this to make it more prevalent. Separate these conductors a little bit. So you can see the wires are separated up here, but then it looks like they're tinned for a certain portion. It kind of makes sense because the barrel on that lug is so tiny. Can you imagine trying to get all those little hairs of wire to go into this little barrel here? So it was a part of the engineering to probably just dip these or tin these wires along the length. And I started to wonder, well, I was getting worried because I thought, well, my repair has to accommodate a lot of heat. But then I thought to myself, well, did they tin it? Or is this because the wire itself is tin coated copper? Because that's what it is. It's tin coated copper. Then I wondered to myself, well, what is the melting point of tin? I found out the melting point of tin is about 450 degrees Fahrenheit. I didn't know that, and I deal with a lot of tin coated copper in power and telecommunications. I've got a lot of bus bars that are tin coated copper. If I can find a quick sample. Yeah, here we go. Here we go. This is copper, but yet it is, see if I can wire wheel it. Here we go. And you can see that it is copper. Hopefully. I did the grinding right there. I was really surprised that tin melts that low. Very surprised. I just didn't know. Okay, I missed that day in school. So I got, because what brought this to my attention was I need to be able to make sure that when I make these connections, there's future liability that I can be comfortable with, that the repair I do is not going to fall apart inside this heated area and cause someone to get electrocuted. So then I got curious about the specs on it. It says it's 1,000 watts and it is 110 to 120 volt rated. And I wanted to know, well, how many amps is that? So what do I know? Ohm's law tells me that if I know my power, which is watts, and I know my voltage, I can determine how many amps it is by going, here we go. Oh, well, yeah, let me do that second. First of all, I was kind of curious as to how many ohms was in this element. So Ohm's law tells me if I want to solve for resistance of the heating element, I know my watts and I know my voltage. I can solve for current over here. I could do power over I squared. I can do, for ohms, I can do E squared over power, or I can do E over I. So I don't know what my current is yet, but I can solve for that real quick. Because to solve for power, all I got to do is go, it's power divided by voltage. So it's 1,000 watts divided by, let's use 110. That's 9 amps. That's what it's telling me. All right, so now that I know my amperage, I'm going to determine what the resistance is. What is the resistance without measuring it? What should I expect? To determine my resistance, I can use power over I squared, which is current squared. So if it's 9 amps, resistance equals power divided by I squared, then I can go 1,000 divided by, 1,000 divided by 9 times 9 is 81. 12.3 ohms. So my expectation is about 12 to 13 ohms. And I know it's about a 9 ampere guy. What happens when I use 120 volts? 1,000 divided by 120 is 8.3 ohms. The reason why I used the lower voltage is because I knew I would be going more extreme, and 110 volt was not uncommon back in 1954. So now we're averaging about 120 volts, 124, 125. So let's see what that looks like. 1,000 watts divided by 125 volts is 8 amps even. All right, well, there you go. I'm expecting to see about 12 to 13 ohms. And if I do this, set up my meter and go to ohms, zoom in a little bit. I'll set that meter up right here. And that should be good. I've got one element diving down into here and one diving down into here. I'll get on this CAD weld. I'm on resistance. And I'll get on the other CAD weld. There we go. 13.4 ohms. 12 to 13 ohms. So I knew what to expect by way of mathematics. I know I can expect about 9 amps of draw, but in reality, that's where you do design engineering versus application engineering. That's the big difference. There's a big difference between design versus application engineering. Application happens to be, could be theoretical, but leans more heavily toward reality. And whereas design would be the overall design of the system and not necessarily how it's applied to a particular customer. So I started to worry over these lugs because I noticed that they had melty all over them. Like, were they tinned from the factory? Or did the tin melt off of the conductors at its hottest point and start to flow? That's when I did a deep dive to try to figure out what is the melting point of brass. That's a brass lug right there. I wire wheeled the end off. And it is brass. Melting point of brass is 1,700 degrees Fahrenheit, give or take. The melting point of tin is about 500 degrees. Well, is it silver soldered? Lead has a melting point of 621 degrees Fahrenheit. And let me look up the melting point of silver solder. Let me see. Yeah, okay. Silver Silver is about oh, I didn't look up silver. I looked up silver solder. The melting point of silver solder in its worst case scenario is about 1325. Now let's look up the melting point of just silver. Melting point of silver. Oh, I could have looked that up in the uglies here. Hang tight. Let me pause. Yeah, so right here, I've got silver. And it says melt point Fahrenheit. This is my column. And silver says it's 1760. 1760. What I was trying to concern myself with is how do I make this connection safely with durability and insurance that it'll remain connected and not break away in the future. And how do I connect? You know, there's these lugs here. These lugs are made of annealed brass, I'm sure. And if I tried to open up these barrels to extract these existing conductors so that I could connect them up to my new copper and recrimp, am I going to crack the barrels? Am I going to crack them? Am I going to damage them? And I got to think, well, why have the lug at all? I believe that I can silver solder tin my new connections. I believe I can tin these copper connections with silver solder, which has a melt point of 1325. And I can literally create a J-hook, bending it and connecting it up to this screw terminal as though it were a regular electrical connection on an outlet. If this screw comes all the way out, I would prefer to have a external tooth star washer, and it does come all the way out. So I think that's what I'm going to do to make my connections here. I'm going to sandpaper up these pads. I'm going to sandpaper the pads up a little bit and clean them. Looks like those screws come all the way out. And I will actually tin my conductors, wrap them, and I will also include my heat shields and dress that wiring over in this direction here and exit the machine, exit the iron. So let me get that set up and let's get started. Hang tight. So I got me some 400 grit emery cloth here. When you do this kind of stuff, everything, all the little details have to be a big deal because you're servicing something. This can't be confused as a restoration or anything, because when I find an old thing, I put it back to work. I don't restore it so that it could be put on a shelf and become a hanger queen. I put it back to work. Found something in the chickens unearthed in my yard. Anybody know what this is? It's got a cutting blade on it. A pulley. I don't know what this is. It has numbers on it. It says Y102N as in November. So it's Yankee 10102 November. I don't know what this is, but it's a very sharp blade right here. It's still sharp to this day. It's like a cutting device for something. Okay, so that pad is cleaned up. That pad is cleaned up. I've got my cord that I've got to strip back a little bit better. I think what we'll do is we'll overdo the stripping so that I can just have a little bit of wiggle room to trim as I need. Remember the previous lesson learned. Scar the jacket and then try to fold it over to snap the rubber if possible. There we go. Damn. No matter how gentle you are, you can really gouge. I can't let that slide. Alrighty. Start over. There we go. Have you guys been out of frame the whole time? Nope. Looks like I did fine that time. Okay. Got that. Flare the conductors out of the way. Trim this. Trim this. There we go. And let's double check and see if the original heat barrier stuff is going to be able to fit. It does. I might be just fine. That's almost perfect. After I tin it, J-hook it. So I'm going to try to scare up a couple of washers external tooth star washers that fit on these screw shanks. And I've noticed something that I'm wrong about, so never mind that. All right, be right back. Let me get my star washer bin. Okay, so here's my internal external tooth star washer bin. I'm looking for a little dinky star washer. Now we'll grab this wire, and yep, that one fits. I just don't like how it's kind of bowl shaped. I'd rather have two of these. This is an external tooth star washer. And this is a internal tooth star washer. For anyone wanting to learn something new. Now I'm kind of stuck. Do I want to use an internal tooth or an external tooth? I think I want an external. I don't know. I think I can get away with this. It's got more surface area. So there, one's zinc and one's silver. Wonder. I don't want to do an unmatched set if I can avoid it. So let me pluck the next. The next one I find is going to be gold zinc coated. Okay, good. Why is that so bowed? I guess I could hammer it flat. I kind of bowled out some of them. I just don't want to hammer them out, because that defeats the purpose of the star washer. Okay, so there's a silver one. All right, we're just going to go with two silver ones. That's what I'm using. Right there. Put these back. I have 168 bins where different things can be stored and stowed, categories of stuff. There's my two screws. I won't be needing those anytime real soon because I got to set up for tinning. So let me do some stripping on this. And I remember I said I used 14 gauge for stripping. Okay. Now this cord is used, and I am looking at the copper conductors and I am seeing discoloration in the copper itself. And it might be hard for you all to see, but there's some browning and some tinging going on there. So what I think I'll do is I will flatten these guys, spread these guys. Oh yeah. These guys, this wire's gotten hot. It's almost like heat sheened. If you've ever seen metal that has the blues and the golds and the greens in it, this is just not your straight up typical freshly stripped copper wire. It almost looks like it has that varnish look to it, like you'd see windings on a motor. I'm going to try to clean these up a little bit, because every bit of that is heat stress and also possibly corrosion. We'll see how well it takes solder. Let me clean these up. I don't mean to drag you guys through along on every step, but it makes for a long video on my end and takes forever to upload with this slow internet we have. What I'm doing is I'm trading out where I open up the conductors. I'm trading out how I open it up so I can make sure to sand all the hairs at once and try to get them as sanded off as possible to get rid of that varnish look, so that when I add flux and I tin these with my silver solder, it'll take well. Okay. So now I'm going to prep them lightly by going like this. As a matter of fact, I want to prep them with a little bit of flux in advance. Okay, so that's good and juicy. And I'm going to twist them. Just a little bit. Yes, I know I touched the flux. Don't worry about me. I've lived a good life. All right. No, I don't live in California, so you can't send the EPA police over to get me. What I will do is use a little bit of alcohol and a rag, clean my hands off with a little bit, because I don't necessarily want to have that on my hands permanently. But then when you use alcohol on your hands, it dries you out pretty quick. So what do? There we go. You scare up a soldering iron that suits me. This will take a minute to heat up. I'm going to try this pistol iron, but I don't think it's going to work. I just don't think this pistol iron is going to work. Let me prep up, because I still got to heat. I wet my sponge down and I got my flux on. I got some good silver solder right here. I don't need that anymore. I don't need that. And that is possibly tinned well enough right now. We'll re-tin it. I make my own tips for my soldering iron out of large gauge copper conductor. Hang tight. Let me get my sponge wet. All right, got it set up. Let's see if I can zoom in on the actual soldering work. Scoot this over. Got my sponge ready. It's got a little bit of water in it. So when you tin your soldering iron, you're going to have a nice, bright and shiny area like I've got right there. I won't zoom in yet. Let me do something different. You got to make sure your tip is cleaned, and that if you hand make your own tips, that you make sure you have a nice smooth chisel edge. And sometimes I'll dip my soldering iron directly in the flux, and I will walk some solder up on it because it'll come right to you. And then go over here and you super cool it, basically is what you're doing. And basically I just tinned the soldering iron. I'm preparing it so it transfers heat proper. So now that tip looks even shinier. Mirror finish. That's what you're after. So now I've got my soldering iron tinned. I've got my sponge right there. I've got my wires already fluxed. I'm going to attempt to get some solder to take on these wires. Start with the whatever one that one is. Need to scoot over a little bit. Make sure I'm in frame. I am. Get some solder laid out. What I'm going to do is I'm going to let solder walk up on the tip right there, the shiny part. And I'm going to let it, I don't know, maybe I'll just heat the wire and feed the solder. Let's see if I can do that. I generally don't do that. And this is the proper way to do it. So let me do this. I'm going to heat the wire up, and you may or may not hear it crackle, but you might see it boil. I'm holding the heat on it to see if I can get that copper heated up well enough to take the solder. Okay, this iron's not cutting it, I don't believe. Let me add some more flux. Otherwise, I gotta break out the bigger iron. Yeah, that's taken. I see it walking. Now, one of the things you need to do when you tin the end of a wire, you need to be real quick about it, but you have to go and shake it off and get rid of any beads. Get rid of any excess like that. You take a look and see if I'm satisfied with that. That's sufficient for what I'm trying to achieve. I need to keep going and add a little bit more though. So I'll get some more flux. Put me a weight on. See if you guys are in the game. Barely. Move you to right here. Barely the right soldering iron for this. Get some more flux on there. You're not soldered good unless it's a mirror finish. I'm knocking off the excess that way. That way you don't have any little beads. All right, let's take you to the camera and show you what I've achieved. You have to have flux when you solder. All right, so that is a beautiful mirror finish. If your solder does not look like a mirror finish, it's called a cold solder joint because you have failed to heat the surface you're trying to solder up to an appropriate temperature. The flux serves as an etching compound and an acid to clean the surface so that it actually takes the solder. Let's get the other one. Now that we know how much solder we need, flux we need, I might as well prepare for that. And overload this guy. Leave a little bit on the screwdriver for later. Lob me off another piece of... I hate wasting my silver solder because this is the good stuff. Find the side that's tinned. Wipe off your soldering iron. Always keep your soldering iron wiped off with your cold watered sponge. Check and make sure you're in frame. Yep. Make sure I don't get in your way. I get lucky on this one and get it first go. Got a nice pool of flux right below me. That flux helps that solder walk into every strand. Take a peek at it and see what I've done. Oh, I've got a bubble on this side. See, it's what you don't want. You don't want a big old blob hanging out there. But while my temperature's up, I'm going to lay it back in that flux puddle. Go back to heating again. Work it in. Keep the heat on. Watch that solder change to a flow. And then hit it. That'll knock all your excess off. All right, that looks sufficient. So there's my second one. So now I'm tinned. And now I'm just going to clean off with alcohol. I'll show you how I do that real quick. Just take the cap off. You got to have a magnifying glass when you do fine detail solder work. Yeah, maybe you don't need glasses, but the more you can see, then it's good. I'm just going to dunk these down in there. Okay, that serves as cleaning. Wipe it off with the rag. Clean the workbench off a little bit. Okay. That'll evap off. Put the cap back on this. The cap back on my flux. My hands have no debris on them. No problems. None of that flux on me. Unplug the soldering iron. I'm going to hang it up somewhere where it can cool off. All right, back at it. I think it's time to fish this through, but we need the parts off the old cord to learn how that works. I should actually J-hook these first. No, because I've got to fish these parts through off of the other cord. Remember this from part one? There's a washer. And there's this guy. And I don't even know if this is going to fit my new cord. I got to pull these guys off. Oh, it barely fits. I mean, barely. It's kind of like it was made for it. Okay, I can live with that. And that washer goes on there. And I'm going to fish these guys on. temperature deflectors. All right. It'll take me a break. Hang tight. All right, break time's over. Union break. So I'm going to fish this back through. Get myself set up for success here. I don't need this here anymore. There's nothing I can use. All right, this one's out to my boys. There's nothing here I can use for something one day. Nothing. It's trash. But it will go in the scrap metal bin. Alrighty. Let's see if we got our procedures down correct. I've got my 2 screws. Got my star washers. I don't know. Alright, so that's neutral and that's hot. So I assumed hot comes in on the... You guys in frame? Yep. I could zoom out a little. So my assumptions were that... I need to wipe this off. Power comes into the thermostat potentiometer. So that's where I'll land my black conductor. Right there. So now I've got to J-hook it. As tiny as possible too. Let's see if that's too small for that screw. I got to open it up a little bit. I might have gone a little too small. Dang it. All right, so that's what we were after right there. I just don't know if I have enough room for a star washer because there's a sufficient amount of thread sticking out, but that star washer is going to be really thick. Maybe I can form this around the screw head. Without damaging anything. Should at least try to see what it looks like with a star washer. Wow. See, the more stuff I add, the less threads get included. Yeah, that's going to be borderline. Let me J-hook this one. See if the screw fits. Open it up a wee. Yeah, I kind of like that. I'll go ahead and put the star washer on and screw it on. All right, am I ready to terminate? So the black is on the left and the neutral is on the right. Make sure you guys are in frame. Show you what I got. There's about 3.5 threads sticking out, and this is like 1/16 inch lugs. I think after I tighten it down, it'll be perfectly fine and flush. There's my black. There's my white. So the black is going to go on the potentiometer side. I'll land that. That's a lot of pressure I had to put on that. I didn't screw up the calibration. Shouldn't have. Yeah, that's sufficient. I'll put my neutral down. Okay. Now I need to sneak some memory cloth in there and clean those contacts like we talked about yesterday. There's a 400 grit here. I'll rip it and fold it long ways like this. I'll try to sneak that in there and work it back and forth. Easier said than done. Should have done that before I made my connections. Well, doubling it up ain't gonna work. Come in with a single, maybe. Holy cow. Wow. What do I have laying around that'll work better? I got fingernail file. Probably snap this off. Get down to some good meat. There we go. That even gives me a nice sharp edge to scrape with. If I can slightly bend it. I'm going to give it a little bit of a bend. A bit of a bend to get in there. There we go. Doing my best as I can to clean those contacts. There's not much filing material left on this file, and I can't seem to leave well enough alone. This one's got some better filing material. I've got a lot of fingernail files here. Here we go. This one's got lots of good stuff on it. Need to break it off. Ooh, that's going to work out so much better because it bends easier. Ooh, that's going to be perfect. I'm going to feel much better because I can get in there and actually sand. Look at that. Perfect, and it's got a lot more grit on it. Lots more grit. I can get it at the proper angle. This video is going to be way too long. No one's going to watch a video about fixing an iron. I'm cleaning right now these guys, the contacts. The thermostatic switch / power on and off switch. Cleaning those, sanding them off a little bit. Because remember, when that lower arm deflects downwards and disconnects due to overheating, as it cools back down, it slowly reforms and approaches the contact again to deliver power, and there will be arcing when that occurs. I'm adjusting the top contact to where it's barely touching, and I'm backing off about a 32nd of an inch so I can have friction on both contacts at the same time. Kind of like cleaning points on a old points type distributor, or points on a well pump switch. That's what we're dealing with here. If these contacts are dirty, it'll draw more current because there'll be a high resistance point, and it'll create more heat right on this particular section of the wiring. So if you can get that cleaned off as best as possible and have good metal to metal contact, you'll have lower resistance. You don't want your hot spots to be on your electrical connections. You want your hot spot to be through your heating element, through the base of the iron. Otherwise, you have an iron that does not get hot enough, but you got something else failing somewhere else. I could have took the tank off, but I chose not to. That worked out real nice. Let's see if we can entertain the idea of letting you see that again. Contact, open. contact, and it turns down. Open circuit. All right. Let's try to slip this thing down over and fight that screw in. I should modify this handle with a file real quick so that that screw can be easier gotten to. I think I'll do that. I'll improve the original engineering flaw. Hang tight. I'm going to round file right here. I think I know what to do. No, it won't help none. Nope. Let me just try to send it. Do I have everything I need? I do. Make sure there's not too much slack. So that's the current state of my conductors right there. This is how I envisioned it. I've got one conductor that's kind of in the way or acting askew, but I got it massaged. Now, what's stopping me from going down? Okay, time to put a screw in it. Time to figure out what parts I forgot to put on. There's that. There's that. There's that. There's my one single screw. Oh, that ain't gonna work. And neodymium magnet. What? Oh, for Pete's sakes. It's not a steel screw? Sure would like to be able to just drop that bugger in there. Everything's got to be difficult. I'm going to try to do it by hand. My fingers are just... Fine. That worked. This is the stupidest thing ever. I bet I'm cross-threading it. Okay, come on. I'm not going to make you watch me do this. Hang tight. Alrighty, got it on there. Let's see, how did this go? Okay. Where the fuck did this go? Where did that go? Come on, guys, tell me. Hang tight. I gotta take it apart again. This goes on top of the water tank. Be back. I got it. Right where it's supposed to be. Witness mark. There we go. Where's my croissant? Told you this video was going to be too long. I suppose that's tight enough. All right, now I get to put those little wedge things in. My flat washer, which is on the cord already. Try to sneak these in there. Again, rubber cord. Let's see how that works. Oh boy. Looks really tricky to me. Oh yeah, that'll go. Some fighting, it will go. Oh boy. Whew. Goodness gracious. I got it. That's properly strain relieved. Oh my goodness. Now it's time to put a plug on the end. Hang tight. Let me find one. Let me produce my bin of plugs. See what we can scare up out of here. Oh, I gotta put the knob on yet. That should go on no problem. Yeah. I could use this, but it's not 3-prong. Nope. I gotta use this right there. I'll organize this later. All right. It is not 3-prong. Set the iron down on it for a weight. Get this slack out of my way. Let's begin the procedure of stripping the wire. Looks like I didn't damage anybody, which is good. These are cheap ass connectors right here. I never buy cheap electrical stuff, but the one time I did, it's right here in front of you. See, it doesn't even have a place to tie off your strain reliefs inside here. I have to cut them off. Normally there's a place inside of a real good plug You can strip this wire way back, and you can tie off your strain reliefs to this. That way when you pull on the cord, you're pulling on the strain relief and not your electrical connections. All right. Well, that's because they've got a strain relief right here built in. Tiny little opening. So that'll do a good job of pinching off that cable. Of course, I can't make use of that. I have to rip this out. There we go. Yeah. I'll leave the rest of that in there. Okay. What are we going to do here? How much room do we need? Probably going to have to strip these real close. Yeah, that looks right. .14 gauge. Okay. So this is how cheap these are. Normally your hot screw will be brassy color and your neutral will be silver, and then you can't mess up your third prong. That's how cheap they are. They didn't designate them. Okay, I designated them though. I put an orange dot on which one was hot. There we go. Okay, so this one's hot on your right. So I'm fishing it in there. Got some plastic flashing in the way and my washer won't back off. There we go. Alrighty. Let's pull this up here. Drop in my screws. These screws normally don't come out on good replacement plugs. Got a third screw that went AWOL on me. Did you guys see where it went? Oh, there it is. Put this on. Should have had that thing on by now. This will apply clamping pressure around this neck right here. To act as the strain relief. It's always nice to put your screw heads pointed down toward the ground prong. All right. Well, that just ain't worth a flying flip. See what I mean by cheap plugs? No clamping force. I'll never do that again. I'm going to have to back this off and wrap beads of tape around it. I'll show you my mod. I'll pause this. Hang tight. Okay, a way to solve this is to shim it. Nice healthy bead of electrical tape. There we go. Alright. So let's get our trajectory right, because these plugs only go on one way. I'm glad to get this thing working again. Let's see if it works. I got to put the knobber jaw back on. It might be sitting around idle for a while, but someone will come across it one day. It might get put back to use full time. Come on. Now I've got enough shim in there to shim it. Shim stock in there to provide the proper strain relief so that's not half-assed. Speaking of half-assed, I should have tinned the ends of these wires. I won't take it apart or anything to do that. Leave that to the next guy. All right, there's my plug. Let's get that knobber jobber back on. I remember in the first part of the video we had a witness mark, so we got to find it. There was only one witness mark. Which size was it? Is this guy here? Let's see my witness mark, so I will best guess estimate that. Okay, that's it. It's off. Let's see if it gets hot. Okay. Right now, it's plugged in, and it's in the off position. I don't feel it getting warm. You'll get a little bit of water. All right, moment of truth. We're going to turn it on. Oh boy, it's getting hot. I've got a hot cloth here. I don't understand the knob. Oh, there we go. Rayon, dry, or steam. Oh yeah. It's back from the 50s. Well, now all I got to do is just wipe it down and put it away. There we go. I'm going to let it sit here and see if it malfunctions and give it the sniff test and all that. Make sure everything's good. But you guys have a great day. Sorry for such a long video. See you later. Enjoy, and don't forget to have a great day.